morning, good afternoon, good evening, wherever you are watching this meeting. I'm Professor Alysson Diógenes from Universidade Positivo, Brazil. I'm from the graduate program in environmental management at Curitiba, Brazil. Today's class theme will be energy, autarky, and nutrition recover in water sanitation systems. Before we begin, I'd like to present some facts and to put us in some Brazilian context and talk about how we're gonna do during this class. Today is the 9th class, and it is the first and only one in the Southern Hemisphere. Well, it's natural. I mean, it's no wonder, because in our world, most countries are at north, but something's different, and I appreciate your patience. This context part will take only about 10 minutes, because by now, hemisphere, there should be springs, and I've got this lovely picture from Edmonton, Alberta, at Canada. They got cherry trees, and the cherry trees got lovely flowers. Everything is so beautiful. It's starting to get warm. But here at Brazilian South, it's autumn, and our backgrounds are some sort of these. The leaves are getting red, are falling. We've got some wind, some chill. And I got the weather forecast for Curitiba and for several other cities for today. At Washington, D.C., we've got 21 to 28. At Beijing, we've got Ni Hao, China friends. We've got 18 to 28. Hallo from Germany, from Deutschland. We've got 10 to 20. At Edmonton, we've got 11 to 22. At Mexico City, 13 to 14. But at Curitiba, where I am just right now, I've got 1 to 14, and without any heated buildings for cultural reasons. That's why I'm using a leather jacket, shirt below it, and my thermal shirt below, because it's really cold. We got no heated building. It really feels like this guy here. But you know, sometimes the forecast misses something, and today, when I woke up to come here, we've got 0, and it was still night because the winter's coming. Game of Thrones was right, Ned Stark, and we've got 0, feeling like 0. Well, they didn't miss that much. Talking about Brazil, we actually write it Brazil with S, not with Z. It makes no difference, just a curiosity. It's a really big country. We've got 8.5 million square kilometers. Just so you know, Europe has around 10 million square kilometers, and South America has about 17 million square kilometers. So Brazil is almost half of South America. Brazil has a part of its country in the northern and a part in the southern hemisphere, and there is the 10th to 15th world economy. It really varies a lot. Since we are so big, sometimes we grow a little, we get the 10th place. That's where we are just right now. We've already been the 7th, and we've already been the 15th. And it's really big. We've got a lot of people. It's not like the richest country in the world, but it feels like it's nice. It's 212 million people. It's divided in 27 states and 5 regions. And when you hear about Brazil, you probably think of this. This is the Amazon picture from Amazon rainforest. And then everything you can see here, woods, we've got a river, and it's very and everything else. Or maybe you think of Carnival of Rio de Janeiro, and Rio de Janeiro might be the capital from Brazil, and everything about that is wrong. I mean, it's not that that doesn't really exist, but Brazil is way more than that. It has a diverse weather and diverse culture. We are talking about the 5 regions here. We got North, Northeast, Center West, Southeast, and South. The North is hot and wet. The Amazon rainforest is right here. The Northeast tends to be hot and dry. Center West, Southeast, and South, I mean, it's complicated. Temperature varies a lot. It can go to -10 to 45, depending on where you are here, and depending whether it's summer or is it winter. It really can be challenging. I mean, just not for building, but for our health, because you can. Yesterday we had 20, and now it's 0. It's a really roulette. Talking about Brazilian forests, we've got obviously the Amazon rainforest. I mean, it's here in the North region. It has about 3 million square kilometers, and it's not all of the Amazon rainforest. We got Amazon in the Guyana, in Suriname, also Venezuela, Colombia, and Bolivia, and Peru. All of these countries, they have some part of the Amazon rainforest. And so 3 million of it approximately are at Brazil. The weather is wet, really wet. They've got lots of rivers, and it rains a lot. It rains almost every day. That has some cities right around here where you can really set a schedule to before the rain and after the rain. A typical animal would be the jaguar, the onça pintada, and it's a very typical animal. These are huge felines, and they can go to 70 or 80 kilograms, and they can easily kill a person, but we are not in their menu regularly. I hope not. I hope they just keep eating some swines and other things, some monkeys and other animals that live in Amazon. Other biome or forest would be the cerrado. Cerrado is a Brazilian word for closed, and it's very interesting biome. It has around 2 million square kilometers. It's dry, but it's also very fertile ground, and a lot of our grains come from this region. It's this yellow region here, and we've got several soybeans planted here, and corn, rice, and most of our grains come from this region here. Also, they've got lots of cattle, or ox and cows are being raised here. And these are typical animal from this region. It's our Brazilian wolf called the lobo-guará or red wolf, and it kind of makes sense. He's sort of red. It's smaller than the wolf you are used to in North America, or some other wolves that happen in Europe. It goes to 90 centimeters, but it's a very beautiful animal if you have the privilege to see them. Then we got the Atlantic forest. Since Brazil is in the Atlantic Ocean, we've got the Atlantic forest. By now it's yet very degraded. Once it was that dark gray, but now it's this light green. As you can see, there are just some spots here, but yet it is around 100,000 square kilometers. We've got. Hello, Shu. Oh, okay. Thank you for muting. Anyway, just I'd like to talk to you. If you have a question, you may anytime raise your hand, and I'm going to answer your question, okay? But let's go about Brazilian context. And yet it has around 100,000 square kilometers. That's a picture of a train that goes out from here, from Curitiba, and goes down the hill to the littoral. And it's a very beautiful picture. I've been to this train a couple of times, and every time it's a different experience. It's really worth it if you're at Brazilian South. Then we got the Caatinga biome. It has around 730,000 square kilometers. It's unique and exquisite. I mean, it has nothing like that in any other country. During summer, where it's dry and gray, everything gets just like that. And the typical animal is the donkey. The donkey was very adapted to this reality here. However, whenever it gets the first raindrops, it gets really wet and really green. I mean, it's beautiful. I was born in a state that has Caatinga. It's incredible when the first raindrops come, everything gets green. The background changes completely. The soil is very salty. I mean, if you really get a random stone from the ground and lick it, it's really, really salty. Someone from geology might say that because it was an ocean, a very ancient ocean, okay, but it's really salty. The animals there are goats, and also we can plant grains there, making some calcium correction, and we can plant grains there. It grows really nice. And of course, since Brazil is so big, there are so many others. I quoted you, the Pampa and the Pantanal. The Pampa is in the south. It's really flat, and the background is just like that. And Pantanal is wet and nice and warm. They've got the alligators. They are very beautiful, and some caves just like that. There are lakes with fish. It's really nice place to visit. I mean, you can go to Brazil, you can live here, and never you'll be able to visit every single nice place to go for tourism or for research. I mean, really, if you want, come here. You check by yourself. About our relief, Brazil is a hilly country. We call them Serra, and bikes are not as popular as daily transport just because our cities are just going up and down. We have just a small part of the country where it's really flat and would be nice to ride by bike. We have all these yellow parts here are parts where we are up of some hill somewhere. And I'm here in this red spot here, Curitiba. I'm really at the Brazil South. We are at some of the highest cities at 900 meters from the sea. It's a very unique climate because we are just 100 kilometers from the sea, but in some of high altitude. Of course, it is lower than Chile, it's lower than Peru. They've got a set of mountains here, but for us, Brazil, it's some of high. Brazil colonization, I'd like to say that everyone can be Brazilian. If you want to be Brazilian, we don't have a standard face. I mean, you look at me, maybe you think I was from Portugal, and probably my ancestors came from Portugal. However, my last name is really a Brazilian name, because when the guy from Portugal came to Brazil during the 17th century, he married an indigenous, and he mixed my family. But in Brazil, We've got 80% of our colonization from Portugal, Spain, and Italy, and 15% from Germany and Japan. And we've got a lot of countries with less than that. It's like Ukraine, Lebanon, Switzerland, China, all of Arab countries, Israel. We've got some sort of huge colonization. And every time a country is having some issues, they want to come to Brazil, they are welcome. I really mean it. Everyone can be Brazilian. Also, if you are missing the indigenous population, the indigenous at Brazil, we had that when Portugal came here at first, they've become very miscegenated. This is a picture from a guy who lives at Caatinga at Brazil. And if you know what I'm talking, that guy is not what you would expect from an Indian. And that's really like some other random guy at Northeast. But that's because you've got a very miscegenated population, and that guy can be just a regular Indian. And this guy here is from North region. That could be an Indian, but you know, he is also incorporated in our civilization, and the population just got miscegenated. All the Indian are among us. I'm part Indian, and we are doing fine. Talking about Curitiba, our population is it's almost 2 million people. There was from 2021. We are here in the south region of Brazil at the Paraná state. It is the 80th most populous city in the country. The demographic density is for like 4,000 inhabitants per square kilometer, and it has several beautiful parks. I really enjoy this one here. It's the Tingui Park. It has a beautiful waterfall. It has several ducks. It has this beautiful cave here where you can go around this formation here and walk just near this waterfall. It's very nice. And we've got some memorial from our colonization at Curitiba, and this the Ukraine colonization center. It has a church. It has some records for Ukraine colonization. It's really, really nice. It also has some Polish memorials here at Curitiba. I mean, our colonization really diverse, but the most beautiful park is the botanical garden. It has this structure here where it grows tropical trees inside, because it's I forgot this greenhouse. It's a greenhouse. It's really nice, and there are lots of gardens. It's flowers. It's really beautiful place to go. Finally, I've got everything I wanted to show you about Brazil, and we are finally reaching our theme, energy and water autarky. Autarky is not a common word. It's usually adopted in economy. It means self-sufficiency from the context we are using now. And we've got the challenge. It's drinking water for everyone. I mean, the world population is growing the last 50, 60, last century after the antibiotics. The world population is really growing, and that increases the water needs. However, the more water we need more energy to purify this water. However, the more energy we need to purify the water, the energy production degrades the environment, which means we have less drinking water. And that's really concerning because, you know, the world population is growing and we need more water. To have more water, we need more energy. But to produce more energy, we degrade the environment and we have less drinking water. And then it becomes a cycle. It's a not a nice cycle. And then we've got a really big challenge for the next years. And even worse, we've got wastewater, and wastewater treatment consumes 0.3 to 0.6 kilowatt hour per cubic meter. That might not seem a lot. However, it is 10 times the energy required for water treatment. So the problem's on the table, and we gotta solve it. And our class begins now. I'm gonna bring several comparisons to different countries. I try to use Brazil in most of them. I've used Mexico, Canada, Germany, China, and US. However, if your country is not here, don't be ashamed. I've got the data that I could find, and you can get this data by yourself. And that would be really nice. That would be a nice paper, by the way. Okay, our class structure will be this. We'll go to energy for water supply and wastewater facilities, wastewater treatment, opportunities for energy recovery, water for energy production, opportunities for water conservation, and savings in power plants. We'll go to these 5 topics in the next 3 hours, and hopefully we'll have some time for questions. The first one will be energy required for water treatment. So we are assuming we already got the energy, electrical energy, produced electricity, and then we need water, but not any water, drinking water, water ready for drinking, a clean water, and the same for wastewater. We can't just go there and drop the wastewater in the rivers. We have to treat it before. That will be a really fast topic, but the next ones will be longer. Energy for water supply and wastewater facilities. In US, you've got 200,000 drinking water treatment facilities. That data is from 2015. 85% come from large-scale systems, which are 5% from all of these systems here. And for wastewater, 75% is served by these public wastewater treatment plants. 70% are small plants, which reach 10% of population, and 22% are large plants that can go to 85% of population. What about the other 5%? I mean, 85% plus 10% goes 95%. That goes to 5% of population without the public wastewater treatment. They have another particular wastewater treatment plants and are not listed here. In Brazil reality, we are, for drinking water, we are 7,000 drinking water treatments in Brazil, which reach 85% of the population, and 16% use some small systems here. We've got less treatment stations than would be expected, since in US it's 200,000. In Brazil it's 7,000, but I mean we've got sort of almost half of the population of the USA, and less than 10% of the drinking water system. That happens because we've got bigger ones, since we've got bigger lakes. I mean, there are big lakes in US, but in Brazil, we've got more, greater number of these big lakes that we use to our drinking water treatment systems. Talking about wastewater treatment, almost 50% is treated in public wastewater treatment plants, and the other half go to other systems as septic tanks. I mean, this is really a challenging number, because we will need really need to increase this number here. This is going to the land. I mean, it's filtrated and everything else, but it's not returning to the system. That should be an issue for the next governments. Okay, that was quick. I mean, it's a slow beginning. We just showed some data. Now we are starting part 2. And my recommendation for you is that you fasten your seatbelt, because we are going to accelerate now. The second topic would be energy for water supply and wastewater facilities. And that shows that our conventional water treatment is just the treatment that gets the source water and delivers a clean water. And it consumes about 1 kilowatt hour per cubic meter. When you are talking about desalination process, I mean, this is the regular treatment, but there are a lot of countries or even a lot of regions in countries that you don't have this water here. You don't have this source water. So, but you are in littoral, or maybe it's like my home region, the Northeast at Brazil. Since the soil is very salty, the water inside the soil is also salty, and you got the desalination process. However, this desalination process consumes about 10 to 20 more energy than the regular conventional water treatment. When you are talking about wastewater, you can go to twice as much or 3 times as much energy required to treat the wastewater and deliver a treated effluent. And you know, this treated effluent, it's not like the clean water we are used to. It is water, but it's not ready for drinking. And if you want to make it ready for reuse, you can add more energy in several processes and have a process named water recovery and make this water ready for reuse. And then it goes, summing these two here, it can go to 4 times the energy required for water treatment. If you're not familiar with the concept of cleaning water treatment, I've got some images here. A regular water treatment would go just like that. You've add some chemical to the water, and the raw water might be just like that. It's sort of brown, it has some particles here, and you add some chemicals to coagulation, and it goes just like this, and flocculation, which aggregates these particles, and then it goes to decanting, which already makes the water just like clear, just like that. I mean, it's not ready enough, but it really looks nice here. And it goes to a filtration process, and then disinfection, and then fluoridation, because the fluor, it gets better for our teeth. I mean, this is a Brazilian process. I know in world, the steps would go to 1 to 4, but the fluoridation can be or not. I don't know at your country. Let us participate some. Where you live, do you know whether they put or not this process here? Someone? Anybody?
They definitely do it in some states in the US. I'm not sure if all of them do.
Some states?
Mm-hmm.
Thanks, Alysson. You know, it's very strange reading my name in your name and you are a woman. I know our name can be both man and woman.
In Mexico also, depending on the state, because Mexico is a big country also, and some states have a high concentration of fluor. So some states apply the fluoridation state, but others don't. So,
you know, fluor is nice for our teeth. Thanks, Jorge. Nosotros podemos hablar un poco de español. Okay, you know, fluor is very nice for our teeth, but in the right amount. In excess, it can really be bad for our health because it has some diseases that are caused for excess of fluor. And in Brazil, they had to change the toothpaste formula because we already had fluor in our water. So they had to reduce that in the toothpaste. Following, some plants consume a lot to clean the water. Nearly all the energy consumed is electricity, about 80% for motors, pumping, and transport. And I've got this graph here comparing Brazil, Canada, Mexico, Norway, and US. And what really calls our attention here is the energy range for Mexico, but also at Canada. And that happens because in Mexico and Canada, there had long transport ducts to take water from some place to another place. And Norway is a sort of smaller country than those here. And the water, the transport is not the main issue. In Brazil, we've got some, US, you got some. In Brazil, it's a small amount of energy spent because we have plenty of water sources. And if you are in a city, it's very likely you have a river nearby and you can use that river to get water and make it drinkable. So we don't have that much of energy spent for that. Most of our Brazilian energy is spent in pumping and also some motors for cleaning these waters. When we are talking about desalination, we can use thermal and both thermal and membrane desalination. The most common is reverse osmosis. It requires a lot of pressure, and you've got salty water here, and you've got a permeable membrane. And the more pressure you got here, you can make this water go from here to here, even if here is not as salty as this side here. But the problem here, it requires a lot of pressure. And pressure is energy, and energy is what we don't want to spend. I mean, it's a challenge to reduce the energy to almost the same as the conventional water treatment. That would be great. I mean, that would be great because we have salty oceans around us. And if we can reduce the energy for desalination, we would have water like forever. But that's really energy spent. And also a thermal example, which is also nice, we are trying to make it viable. That one is from some researchers at China. And we've got a passive vapor generation system that can produce 5.78 liters per square meter hour, which is some sort of really nice here. We use the sun to vaporize the water, and it goes through a silica aerogel, a solar absorber, and some capillary tubes, and go to a condenser. And that condenser makes the water pure again, and the salt gets crystallized and goes solid. And that's a very nice number. The problem is that sun varies from time to summer to winter, and whenever it gets really cold, the net value here can reduce a lot. But it's a space, there's space for research. Also, if you got water, it's expected that you've got something to put this water in something. And the most common recipient for this water here would be the bottled water. So it requires some energy to produce it. Since the world is growing so fast with rapid industrialization, the bottled water production is growing really, really fast. And the plastic bottles manufacturing requires 4 megajoules per liter of energy. And that's really a lot, because we've got a lot of liters being required. And just compare these numbers here. For treatment, it's like from 1 kilojoule per liter or to 20 kilojoule per liter. Filling operation feels like the treatment. I mean, we can even see those bars here because they are very tiny. Transportation just requires some more. I mean, it can go even bigger than the plastic bottle manufacturing. And the cooling, because we drink cold water, can have some considerable energy also. But the problems here are transportation and also plastic bottle manufacturing. If you are working on a research that can replace the plastic bottle, man, that would be really, really nice. Also, going to wastewater treatment. Water and wastewater treatment plants account for 3 to 4% of the US electricity utilization. That, you are wondering, well, 3 to 4% are not that big. However, when you are talking about the number is 56 billion of kilowatts of electricity. I mean, it's a really huge number. And any percent you can reduce here, any 0.1% you are reducing, it's a huge number of kilowatt you are reducing. And some communities where water and wastewater treatment plants can go between 20% and 40% of total energy consumption. Reducing it is very important, not only in US, but worldwide. I've got a graph here from the low, the medium, and the high energy consumption values for wastewater treatment plants varying size. It's really interesting because the treatment energy requirements generally decline as facility size increase. And even more, if you divide the number here per million gallon days, and you can see that wastewater treatment plants, a small one with less than 1 million gallon day, the lower requires 620, and the highest goes to 2,000. However, if you go to the other part of the graph, if you go to the more than 20 million gallon day, you've got the low requirement as 120 and the big one to 2,000, which is the same. I mean, it's nonsense that this one is processing 20 times more wastewater than this one, and both of them require the same amount of energy. And that's because the technology also changes, and these technologies here are more effective. However, the disadvantage of this here is that you have to transport the wastewater to them, and this works better for big cities. Several countries have initiatives to reduce the energy consumption for wastewater treatment. When we are talking about Austria, they have a strategy of preventive maintenance, which already reduces the energy from regular wastewater treatment, reduced in 30%. Belgium and Brazil have variable speed driving pumps, and that also has a very nice effect of 15 and 33% reduction. France uses organic fuels to process the wastewater, and has a 88% of reduction in the fuel fossil consuming. It's really nice. Mexico has water pressure regulation, which causes 27% reduction in the regular wastewater treatment, and USA uses photovoltaic systems that reduce the purchase of fuel fossil or electricity for the comparing to the regular treatment. Also, during this class, I don't know how familiar you are with wastewater treatment, and so I spent a few slides talking about some techniques. I mean, there are lots of techniques for wastewater treatment. We'll just check some of them. I think it helps us to bring the case to our reality and then make everything more near what we need. First one will be the lagoons. Are pond-like bodies of water or basins designed to receive, hold, and treat wastewater for some period of time, some predetermined period of time. In the lagoon, wastewater is treated through a combination of physical, biological, and chemical process. Here I got this picture from Norway, where you can see a wastewater treatment lagoon, and you have a truck here, so you know the size. Probably they are building some new lake here, and the wastewater, these are probably 2 ponds, or maybe it's our aeration process, and they are treating a wastewater. You can see that this one's really dark and this one is changing colors. Probably they are putting some chemicals here, or maybe they are doing the aeration of the wastewater, and it really changes the color of it. And as you can see, it's a very complex system. I mean, it's simple. It's just put it there, put some chemicals, let it rest for a while. However, this wastewater here cannot in any way permeate to the ground. I mean, there are some plantations here, and you don't want to eat, to seed and to grow your food in contaminated soil. And so if you are treating wastewater here, you must guarantee the wastewater stays here where you want and where you can treat. Another technique is the trickling filters, or TF. I use it to remove organic matter from wastewater. It's an aerobic system that uses microorganisms attached to a medium to remove organic matter from wastewater. It feels like these ones. I mean, the drainage system goes here, and these pivots here, these arms are rotating, and they are spreading the wastewater here, then go to some stones to filter it, and what comes down here goes to the effluent size. And it's just like that. And these arms are rotating, spreading the wastewater, and the wastewater is filtered in these stone beds, and the effluent goes to another type of treatment. And you can also have this one mixed. I mean, you can make a primary treatment in lagoons, and then go to TF, and then come back to lagoons to a different type of treatment. The most common process for wastewater treatment is the activated sludge process, and it involves blowing oxygen on air into raw, unsettled sewage. This process smashes the solids and make everything more processable. Live bacteria sit on the bottom of the tank, and the dead bacteria flow to the top. Clean water is discharged in a soakaway or a water course, while the live bacteria return to the digestion chamber. It's not the most beautiful image you'll see today, but it's more like this one. we've got these aerators here, and everything is being aerated. The solid parts of the wastewater will be broken. And I hope this dog here is not drinking from this water. I mean, if he is, he's just like an iron dog, which health cannot be broken. Okay, and we've got the advanced wastewater treatment. It's any process that reduces the level of impurities in a wastewater below some threshold or some secondary biological treatment. It includes the removal of nutrients such as phosphorus and nitrogen. Both of them are very important to us. They can be used as fertilizers in a high percentage of suspended solids also. Oh, Shaoxiang, yeah, evaporative crystallization, yeah, that probably was from the desalination plants, right? Okay, I've got this slide here that Aura had presentation animation. Let me just put it back. Okay. I'm sorry for that. And we are back. And our advanced wastewater treatment, we've got these very interesting study case from Kreutzig et al. 2021, which they are using the wastewater through hydroponic system. Of course, they are not just taking the wastewater treatment plant influent and using in a hydroponic system. The wastewater goes to a breath chamber, and then some part of the wastewater already treated goes to the expander granular sludge bed reactor, and then to a sequencing batch reactor, and then to a biological activated carbon filtration. And these ones goes to the hydroponic system. Why is that? Because wastewater has not only everything we don't want, it has a lot of things that can be useful to us, like phosphorus and nitrogen. And you can use those fertilizers to a hydroponic system. And getting some water here from after the aeration tank, sedimentation tank, ozone reactor that kills everything, you can use them to a hydroponic system, and the effluent goes back to aeration tank. I mean, it's very interesting way to use the wastewater. Also, the energy for wastewater treatment, we were already talking about that a few slides ago. It can go analyzed by consumption method. Another alternative would be the biogas production that would reduce it up to 50%. The treatment by lagoons is the smallest energy as expected, because you are just like letting the wastewater in a lagoon and using some aerators to get it better, but most of it's just staying there in the lagoons and being treated from one lagoon to another. When you are using trickling filters, the energy required for that increases some, and if you are using activated sludge, it goes really bigger, it goes to 0.6, and advanced water treatment surprisingly consumes less energy than activated sludge. I mean, these are very new techniques that use both chemical and biological processes, and we try to recover the nutrients. And all of these, we are not trying to recover directly the nutrients. It's not the objective. The objective is to have some clean water and just clean enough to go back to the river. However, here, it's a very interesting process that we are really trying to recover something from the wastewater, and it is cheaper, energetically cheaper than the activated sludge. Keep that thought. Energetically cleaner or energetically cheaper. Just keep that thought. And we've got here the energy requirement for conventional water and wastewater treatment operation and processes. Here's the entire process. I mean, we've got the river, and after the river, we've got some energy here for pumping. We've had some alum, some polymer here, rapid mix, flocculation tanks, sedimentation, drying beds, waste backwash filter, and then we go to high pressure pumps. And after we go to high pressure pumps, we've got the city. After the city, it's not anymore water. And looking at this graph here, you can see that the two most energetic consuming steps are exactly as I said, the pumps. Pumping water is a really energetic consuming process. The other process are energetic consuming, but not even half of the pumping process. Okay, then we got the city, we drink the water, we go to the restroom, and then we have the wastewater from a city. And then we go again to a pumping, we go to the cleaning process, we've got the activated sludge, which consumes a lot of energy, and then chlorination, then it can go back to the river, but we already have some other process that can produce cod, we will talk about that, and go to incineration or disposal. Here we've got the solid part of the wastewater, and here we got the liquid part of the wastewater, goes back to the river. Oh, and this process here is more energy consuming than this process here tends to be. Then we got a paradigm shift. Wastewater was every time in human history a problem. Waste is something we don't want. We don't have anything to do with it. However, when we are talking now about wastewater treatment, a sludge process, activated sludge process, is so energy intense and chemical consuming, and it has lots of problems of dealing with excess sludge disposal issues that, and even worse, the chemical and biological nutrients removal is energetic intensive. So it can really create panic when we are dealing with that. But we are having a new goal here. It's not treating the wastewater as a problem, but changing the plant design to operations that should achieve existing public health system and new environmental goals, maximize energy and wastewater recovery, and preserve and recover nutrients for reuse. It's really a new way of thinking of treating wastewater. Those goals are obvious. I mean, everyone would think just 10 minutes would reach these goals here, but how can we do that? I mean, it's easier to say than to do, but we can recover some energy. Looking at this graph here, the energy required for treatment is around 0.75 megajoules per liter. However, we can recover thermal energy from the wastewater around 7 megajoules. I mean, look at this. You are spending 75 cents and you are getting back $7. That really feels nice. I know, it's a graph. I mean, it's not telling the whole truth, but let us get it some excited. Okay, you can have 7 back. It's just, you know, it just doesn't feel like that pyramids. I mean, you are spending 0.75, but then you are getting $7 back. If you are spending $1,000, you get $7,000 back. Feel like those pyramids, right? But I mean, that's the number. And it's not guarantee you get all of this back. I mean, it's potential, but we can go into think ways to get all these back. You are spending 0.75, getting 7 from thermal energy, 2.72 from extractable energy, we'll talk about that, 0.79 from nutrients, and 1.93 from organics, from solids. If we somewhere get just these two here, I mean, energy for wastewater treatment can already be a liquid energy. We can already have more energy from wastewater than we spend. And already these two here would be great. But let's talk about that. We've got a possibility to from 3 to 13 times recover. Some of it for thermal, using a heat pump, some from chemical, using cod, and another solids. Here I got some example. First one would be the thermal, since it's the bigger, right? We've got 7 here that we are trying to recover. And why does the wastewater has thermal energy? It has. Oh, okay, we've got some chats here. Wastewater can be treated as power of nature, plants. Yeah, Raymond, you are very right. And actually, we'll go to plants, algae, bacteria in future. In this class, we'll talk more about that. Keep that thought. Okay, we've got here a regular bath. I don't know how's in your country, because here in Brazil, especially the ladies, they really like hot showers. I mean, so here it's 38 degrees, but I really like to think that a lady can shower here. It's almost 60 degrees. I mean, it's almost burning her. But let's talk about that. The water would come to 6 degrees and go to a heat exchanger that heats the water to 55 and goes to 38 degrees in a shower. And the wastewater here, just for a shower, is going to 35 degrees and going to the wastewater treatment facility in 22. And what about these 35 degrees? They were going just away, and now they are back heating, preheating the water. These one are used in boilers or something. And for a house, you got the district heating system, and the energy from the sewer is preheating the wastewater just before going to the wastewater treatment plant. That's what we are talking about when recovering thermal energy for heat pump. The conventional, we've got all this water here that came from 6 degrees, goes to 55 degrees using a boiler that's burning natural gas or diesel or electric energy. And that's how we are recovering thermal energy. When you are talking about chemical, you read cod and solids. I'm talking about cod, and I don't know if you are familiar with that. Cod's a small word for chemical oxygen demand. It's a parameter to determine the total amount of organic matters in domestic wastewater. 1 kilogram of cod removed for wastewater treatment plants will generate this half kilogram of dry biomass. I mean, this is a chemical parameter. However, this chemical parameter is associated with dry biomass. So whenever you read COD, you do not read chemical oxygen demand, you read biomass, because that's what we are talking about. 1 kilogram of COD is half kilogram of dry biomass. And COD comes from activated sludge treatment plants. Whenever you've got wastewater, you go to the activated sludge. Some of it generates CO2, however, some of it generates the dry COD, and it can go to biogas and goes to burn to generate energy, or it can go to generate fertilizers, and it means biomass. So what? That's it. Produce biogas, burning power plants. I mean, we've got COD. If you've got COD, you can do energy from methane, or you can have nutrients. But what we are talking here is for energy production. And then that production, this is a paper from 2016. You may have this potential here for energy recovery. And then again, we're having an energy gain here for everything else. So wastewater can be treated as money because you are spending this and you are getting this back. Also, you have total suspended solids. Any solid in water can be trapped by a filter. That includes a variety of material like silt, decaying plant, animal matter, industrial waste, and also sewage. High concentrations of these can cause many problems in health and aquatic life. So we gotta take this off the water before going back. The process in these wastewater treatment plants are mostly filtering and flocculations. In our house, it contains food residue, human waste, and other solid material like grass and some fat. Everything we put through our drains goes to wastewater. And the process are filtering and flocculation, and everything that's got back, sequestrated, it can make biomass. But okay, but what we do with this biomass, just like the COD, we burn it, make energy. So what again? The chemical energy ranges from 12 to 15 megajoules per kilogram of COD, and also 27 to almost 30 megajoules per kilogram of suspended solid. That's really a lot of energy. And whenever we are having war in Russia and Ukraine, we are needing energy that really can make a lot of difference. And for something we were just throwing away. I mean, that really should change our paradigm. The economic value of potential product recovered in the forms of water, nitrogen, methane, fertilizers, and phosphorus per wastewater would be 45 cents. But that's a data from 2009. And already in that time, it is most valuable than water. I mean, we've got water, we drink water, and we are money machines that are producing wastewater, and that wastewater is more valuable than the water. It feels like honey. The bees eat something and produce to us honey, which is way more valuable than the flowers. We are sort of wastewater bees because we drink water, we eat something, we produce wastewater, and this wastewater is more valuable than the water. So The paradigm shift is not to treat wastewater anymore as wastewater, but to treat the plants as waste resource recovery facilities. Again, we are trying to recover energy here and to make the waste profitable. We want, and also, there are particularities. In Brazil, it's not common to use water heating system other than electric shower. If you ever come to Brazil, you are just looking, where are the two registers for showers, and you just got one, because the water is heated using electricity. And even more, Brazil is warmer than most of the countries where you live. And that means less thermal energy wasted. Because when you are talking about here, you can recover as much energy as the difference between the intake and the outtake. And since in Brazil, for example, probably at Mexico also, the water coming bigger temperature than 6 degrees, and this effluent here from wastewater temperature does not change that much, you've got less thermal energy available to recover. Okay. So I've talked to you about changing a paradigm on wastewater to water resource recovery facility. I mean, does that happens anywhere? Yeah, it happens. In US, the Tennessee Water Resource Recovery Facility, it's not called wastewater anymore. It's since the year 2000. What's ironic is that they've got a Wastewater Association Plant of the Year award, even if they don't want to call the wastewater plant anymore. However, it treats 75 million liters per day, but it does not produce energy yet. It has projects to produce energy, and that will make it very nice plant, but yet it does not produce energy. But it's also very technological. It's a very nice power plant, wastewater plant. Now we've got an interaction. I'd like you very fast way to make a sheet, share the number of inhabitants from your country and the city where you live, and how much wastewater does the city where you live produces. Try it in cubic meters or in kilograms. Convert it to a mass flow. I mean, am I making it too complicated? I mean, I know there are so many engineers watching this now, and maybe if you don't know how to do that, we can give a brief explanation. But if you're familiar with the mass flow concept, you're gonna divide it in kilograms. The sewage density feels like the same density as the water, 1,000 kilograms per cubic meter, and convert that to a mass flow. Check whether you use some heating system and estimate the amount of energy down the drain. We'll have 10 minutes for that, and put that in a sheet. We're gonna talk a little and keep that sheet with you, okay? Now it's 10:12. We'll have our break in a few minutes, but we've got 10 minutes to that. Go on, hands on. I'm gonna pause. First one to get the answers, just raise your hand. We're gonna chat a little, okay? I'm gonna pause the record. Okay, we got that, our recording. Does anyone finish at the sheet? No? You're gonna fail the test. I mean, after this class here, we got a test, and who didn't do the sheet's gonna fail today. Is that right? Anybody? No? Okay, I'm gonna show my sheet again just to make it recorded. And what we got here at Curitiba is about 2 million people. Let's put it scientific. So, okay, 2 million people around. When we are talking about the consumed water per day, and we are talking about 200 liters per person. That water comes from different sources, not just the drinking water, but also anything we eat has water. And we are talking about these water consumption, but also when we are talking about wastewater, we make out about 150 liters per person, and this goes to this volume here, the seconds in a day. To convert to a mass flow, I've divided the wastewater to the seconds in a day, and then we go to 3.47 tons per second. That's what the wastewater company is processing just right now. And the energy to process, to treat this wastewater goes to 2.6 megawatt, but the recovered energy in the least case can be 7.81 megawatt, which is a very nice amount of energy, even more if it's coming from waste, from something we are just throwing away. I mean, it's not something we are using. Okay, hopefully you've got your sheet more or less like that, and maybe just keep that sheet. We're gonna use it later, and let's go on, because time go by, and let's climb the hill. Part 3 is beginning. Now we are not talking about anymore from energy to process wastewater. We will talk about opportunities for energy recovery and savings in wastewater treatment. A remark: the purpose of this section is not only to sell energy, but also to reduce costs. I mean, we have this energy spent here, but we want to have more energy got back, but also to reduce the spent energy here. That's what I'm talking about. And I've got this video here to talk the Agua Clara, about the Agua Clara treatment. Electricity corresponds to 20% of the drinking water cost, and plants do not possess this potential energy generation. Is that so? Let's watch this video here.
I'm sorry, Professor. Is the video has any audio?
Okay, let's try I so remember. Share sound. Let's try that again.
In Honduras, most people do have access to water in their homes, but most of them have access to water that isn't actually safe to drink. That problem is actually a global problem.
Currently, worldwide, there are 2 billion people that lack clean water sources, and then there are 2 million people that die every year due to lack of clean water.
I realized right away that the technologies that I had been trained in were not going to work in the villages in Honduras, or this kind of very rugged, no reliable electricity setting. And so I took that question back to Cornell, and I decided that I needed to have a course where I could start teaching the material that would be the basis of the design for these water treatment plants.
So although doing Agua Clara is a class, it's much different from most other academic classes in that it's 100% hands-on. We spend 10 hours a week working in lab, and that involves going and running experiments, and having that kind of hands-on makes it way different from other academic classes because it's also really easy to see how it transfers into real-life applications.
Sometimes in class you can go through your whole 4 years in a vacuum of this is just like engineering, science, technology without having any insight into this is how it affects communities, this is how it affects public health, and Agua Clara puts that in perspective for me.
Every January, we bring students from Cornell who are working in the lab to improve the technologies to Honduras to actually see how those technologies are put into place in the plants. Throughout the trip, they work on actually implementing what they've been learning and then also seeing what the challenges are.
Anyway, if the sound wasn't that good, you can check again this YouTube video. You have access to slides, and you can check more about the Agua Clara project. It's a very nice project that I said here, the plants do not possess potential energy generation. The potential energy comes from difference of altitude. I mean, the wastewater treatment plant would be in a high ground, and we would use this altitude difference to generate energy. These projects, the Cornell Agua Clara project, wastewater plants use the soil inclination, and that reduces the use of pumps. The electricity is up to 10% of the drinking water cost, which is really impressive because electricity can correspond to half of it, and that goes to half of the conventional. These strategies are suitable for location with low intermittent access to electricity sources. It's really interesting. Also, in Austria, in Vienna, the wastewater treatment plants discharges this volume here with an elevation drop in 5 meters, and that is used to a vertical axis turbine and generates 175 megawatt hours every single day, which cannot save the country. However, it was waste. I mean, anything we can get from something we are just throwing away is a profit. And then it's possible. Someone's already using it. You can see in the Agua Clara process, but also in Vienna. And we have similar results in the Clark County wastewater treatment plant, also in US, with 2 Francis type turbines, and the net value of system is $60 per megawatt hour, which is profit. I mean, this wastewater treatment plants is not only spending energy, it's generating energy and having profit on processing waste energy. And the government's probably paying them for that, but they are not only getting the money from the government, they are making their own money. And that's incredible. I mean, you are paying for something and you are getting more money from that, it's really nice. Talking about heat recovery, the US Department of Energy estimates that about 235 billion of kilowatt of thermal energy is just discarded into drains, and only 1/10 of that is required to treat the wastewater. A remark, again, thermal energy recovered can be as big as the water temperature difference. So what? Get back to your sheet. I really hope you finished your sheet, but we can use a simple equation. The power in watt is equal to the mass flow that we calculated before, to the water specific heat coefficient times the temperature difference, the temperature from the waste minus the temperature from the room temperature or the environment temperature. Let us consider that 30 degrees, and then recalculate the power for 30 degrees and use room temperature as the average low during winter, the average high during summer. Since there are some of you who are not engineers, the specific heat for water is 4,182, and the unit is joule per kilogram Celsius degree. Our equation is power equals to mass flow times specific heat times temperature difference. So Q equals to mass flow times Cp times delta T. And we've got here Q, let's call it Q1, is the easier one, with a temperature difference from 30 degrees, would be the mass flow times Cp times 30. And that's the power just going through Curitiba drains using thermal energy. However, during winter, Q2, the average temperature would be pretty much like 30 degrees. And during summer, Q3, the difference here, dt would be 30. Here, dt would be pretty much 30. But here, dt would be less than 10. Because during summer, not only the temperature difference gets lower because the water comes to our homes more warm, but also because the room temperature is bigger, so the difference gets smaller. Okay, I've made your homework, but did any of you just, come on. Yeah, thank you, Ruiz. Did any of you, thank you, Jorge. But did any of you got these numbers? Please, I would just like to see in a country different than Brazil. And I'm going to give you an opportunity. Now you can print that. You can print that and use it to help your studies and check if that's okay. Okay, guys. Print taken. Now let's just make a small pause. I mean, it's 10:40. Let's make a 10-minute break, okay? We'll get back from 10 to 11 here in Brazil, a 10-minute break. You know, there had a time I felt like some disoriented. What kind of filter? Raymond, very nice hearing about you again. What kinds of filter materials are often using biofilters in Germany? That's a very nice question, but I am in Brazil. I really don't know which biofilters are used in Germany. That's a very interesting question. We'll have one topic on biofilters in a few slides. Let's see if some of them can indicate to you a solution. Well, there had a time you've seen, I was just like confused. That's because the PowerPoint missed a slide. And I think this slide is very important. So I got back here. It's about the okay, Raymond, no problem. In Brazil, we use algae and there are lots of plants being researched, but it's yet research, and they are not used, at least none that I know, for industrial cases. I mean, I don't know any wastewater treatment facility that is using plants as biofilter, but algae, I know some of them. And I'm gonna show one in this class. But first, let's see this study case in Senegal. It's from the Omni Processor, from the Bill Gates Foundation, and it's very interesting. Let's watch.
Many people saw a video of Bill Gates drinking water derived from human feces. We've now brought this Omni processor to Senegal, where it's doing the job that it was intended to do.
Dakar is a unique city in Senegal. You can have Africa, summarize it in Dakar. It's a bad situation. In Dakar, 1.2 million people are not connected to a sewer line. They have their own facility. And when these pits are full, people can call for a mechanical emptying, but can call also for a manual emptying. Manual emptying is very dangerous. They dig a hole near the household and they transfer the sludge to this hole. And the manual emptier is directly in contact with the sludge. When people practice manual emptying, you have some pathogen who can spread out in the environment. This is a possibility of contamination of population. Mechanical emptying is better. There's no contact between the sludge and the population, and you can transfer to treatment plant. Right now, we cannot remove the pathogen. This is why the Omni processor is very important. Thanks to this machine, We treat 1/3 of the sludge in Dhaka and make pathogen free. We produce several byproducts: electricity, drinking water, and ash. With this byproduct, we can make business from sanitation.
Les bouts de blanche vont devenir excessivement intéressantes. Parce que ce sera une matière première, comme je l'ai dit tout à l'heure. Ce que je peux conseiller en tout cas aux futurs entrepreneurs qui veulent faire des affaires, ils peuvent venir dans l'assainissement.
When I see this machine, my dream is to change the face of sanitation. In all Senegal, in all Africa. Drinking water is life, but sanitation is dignity.
And that's what I'm talking about when I tell you about the making wastewater as a business. And you can have it from potential energy, you can also have by byproducts or something. I mean, it should not be considered waste anymore. It has lots of potential. Okay, we've got this equation, that's where we stopped. Now let's get back. Whenever we have this equation here showing the amount of energy that's just going down our drains through thermal energy, this means that heat recovery gets better in cold countries or cold days, because it only works for room temperatures lower than the wastewater temperature. And of course, that changes during the year and changes daily. And that's a big remark. However, we still have the combined heat and power systems. And that's a little more interesting than we using that in our homes. They use cold generation plants. It's sort of common in cold countries. We've got some hot source or fuel. That heat goes to generate power through work, and the heat can be used to warm water for residential use, and the waste heat goes to atmosphere or to the water. They're classified in 4 types: combined heat and power. That's the case we are studying here. Cooling heat and power for heating district heating. That's nice because they are heating an entire district with that. And building cooling heat and power just for a building. That's sort of like it works. It has a fuel, the fuel is burned, in the burning that makes a vapor, the vapor generates energy, but we still have vapor with some temperature. That vapor can go to a heat exchanger to make the water hot, to make heat for our homes, and then it goes back to a heat exchanger to cold the vapor and make this cold gas go back to water, and the cycle reinitiates with the Rankine cycle. And the problem is that the fuel, it's hard to transport heat. I mean, there's no solution for that. We don't have a heat conductor like we have water conductors. But we still got some cases here at Brazil, for example. I'm going to show you another study case from the Porto Feliz cogeneration plant here.
With its new cogeneration plant due to go on stream in 2010, Lanxess will be able to meet its entire energy needs for pigment production in Porto Feliz itself. To fuel the plant, the company will use bagasse, a waste product from the processing of sugarcane. The ash generated can be used as fertilizer and returns in this way to the biological cycle. The waste gases generated during combustion will be treated. This form of energy generation will not only lead to a neutral CO2 balance, it will also ensure that waste gas emissions are practically pollutant-free. The vapor pressure necessary for energy generation is built up in an evaporator at temperatures above 1,000 degrees Celsius. The highly pressurized water vapor drives a generator by means of a turbine, producing 4.5 megawatts of current. This is enough to completely meet Porto Felice's electricity needs. On leaving the turbine, the steam still has a temperature of up to 300 degrees Celsius and a maximum pressure of 11 bar. Separate pipeline systems feed this steam to the reactors or to the pigment drying facility. By commissioning this cogeneration plant, the Porto Felice site will be able to do without fossil fuels altogether. All in all, a pioneering LANXESS project in both ecological and economic
It's a very
terms.
interesting case because they are at São Paulo, which is not a pretty much cold state. And they are doing that for textile industry. It's very interesting. Okay, another opportunity for energy recovery and saving in water treatment is the biogas production or biogas generation through anaerobic digestion. It can use the conventional activated sludge and costs 25 kilowatt heatman per capita of person. And each person generates this. And the anaerobic digest can produce 30 kilowatt per hour per person. Therefore, we can have a 5 kilowatt hour profit from energy generation. However, the anaerobic digest does not only produces biogas, it also produces water vapor, which is undesirable, and small amounts of siloxanes, which is some bond connections between silicium and oxygen, and also hydrogen sulfide as impurities. Where is it used? It is used in Sweden, where the buses are from public transport are moved using biogas, and the CO2 goes to trees. The trees sequestrate CO2 are burned to produce methane, and the methane is going again to bus. And this is very interesting because the anaerobic digestion produces 1.2 terawatt hour in biogas. 55% of it is used to heat, 19% to vehicle fuel, 8% to electricity, and 5% goes back to the gas grid. It's not, the gas there is not used just for petroleum or natural gas. It comes also from biogas. And this is the energy supply in Sweden in 2016. Okay, here's some of the biogas cleaning process. The electrical conversion efficiency is around 33%, which might not seem a lot. However, it's very interesting for thermal power plants. Well, for some reason, YouTube doesn't want to play this video, and you can go after the class when you get the PDF, the PDF file, you can go to this site. There's this video is there. It's just some talking about the biogas cleaning. It's very nice video. It's very short also. Okay, now let's talk about Brazil. In Brazil, most of this is a real-time map showing where biogas is being produced, and as you can see, most of them are in the south and southwest region. That makes sense because that's where swine and poultry farms are, and swine and poultry waste is using to produce biogas. But that's bad because it's also the regions, the colder regions in Brazil, and cold weather is terrible for biogas production because the bacteria that process the waste and make biogas, they just get so lazy, and even without a TV. But I know it ain't much, but it's honest work. we are doing that in Brazil. I've got a few study cases here. A typical production in Brazil is a poultry farm, and it really produces it has a potential to produce way more, and that is just for poultry farm. For swine, that would be way more production. And that's a typical production. The poultry is here, is raised here, and the waste goes here to a tank, and where there's an anaerobic digestion, and the gas comes here to this storage facility where it's burned to produce energy right here, or goes to the home, or goes to tanks where it can be stored and used later. Also, here at Universidade Positivo, we have a school power plant research, and it just produces a little amount of biogas here. However, everything here is instrumentated. We are using this from ox and cows waste, and we are just processing using artificial intelligence to predict the amount of biogas and pollutants and also impurities that will be generated considering temperature and several others parameters. It's a very nice facility. Okay, Raymond, now we've got the algae growth for biofuels. Usually they need lots of sun and some heat, and again, here in South we are not that much favored with sun and heat. However, it's probably more than most of countries in the world. It needs CO2 and does not have many practical applications for wastewater. However, it uses garbage, which is another waste and very interesting. And if it's not applied to wastewater, it means it can be applied from wastewater, because it's waste. You are not burning it, but the algae needs some organic material to grow, and wastewater has this organic material. Here's the algae growth for biofuels. It gets CO2, it gets the nutrients from water. That's where the wastewater could go, and the algae grow oil and go to dewatering, the oil extraction goes to trans-esterification process, and then you have biodiesel. Notice that is not biogas, that's biodiesel. It's liquid, and it's just like to diesels go to trucks. It's a very interesting process. It's being studied here in Brazil and some other places in the world. Another study case is at Viçosa. It's a city from Minas Gerais at Brazil. Algae processing swine wastewater. In the concept of circular economy, you can have more information at this link here. And also, another technique would be the NMOX process. NMOX is the abbreviation for anaerobic ammonium oxidation. The application lies in the removal of ammonium in wastewater in two separate processes. The first step is nitrification, using this equation here, and the second process, the ammonium and nitrite are converted to NMOX process to and use about 15% nitrate to NMOX bacteria, converting everything to nitrogen and water, which it's way better than CO2 or something. It goes from ammonium to nitrogen and water. It has a lot in our atmosphere. There's the wastewater influent. It's a very high load of activated sludge, goes to flocculation, separates the biomass, The biomass goes to anaerobic digestion, which produces biogas, and the supernatant gets together with the flocculation accident, goes to NMOX denitrification, and then we have clean water. Feels like magic, right? And it's a very interesting process. The advantage is it produces N2, and however, it is highly energy consuming, and it's associated with the production of excess sludge. And as we already seen, the sludge is also very energetic consuming. It produces significant amounts of greenhouse gases, just like CO2 and N2O, and also ozone depleting NO. And also, an advantage is that almost no O2 required. Worldwide, we've got about 30 facilities in 2015. That's a very new process and still being researched. Another one will be microbial fuel cells. That's very interesting because they're similar to regular fuel cells, to hydrogen fuel cells. They're becoming more and more popular due to the electric cars. But instead of metal catalysts, we use biocatalysts with viable microorganisms that convert the stored energy to chemical bonds, generating an electrical current, more or less like this schematic here. This one is really, really new. I mean, the first papers I could find with practical applications were like from the last year. And it has an advantage of operating in ambient conditions. It can go work in low temperature and work with several substrates as fuel. It was a graphite or carbon felt where the bacteria stays. In an aerobic mixed community, there are lots and lots of bacteria we use it for this. The bacteria will be here. The swine waste will go through this felt, and the bacteria will produce a difference of potential, electric potential, and you can use that as a power source. It's a very interesting process. One possible arrangement would be like that. The waste goes to a primary clarifier and then go to the bacteria which produce electricity. The second clarifier goes to the anaerobic digester and produces biosolids and biogas, which is not processed, goes through the waste treatment. However, this should be very profitable also. A reflection up to now. Yet nothing compares to fossil fuel. That should not discourage us. Actually, that should encourage us to keep researching. Of course, none of us was born during the 1900s. However, there had news everywhere. There's a print of the New York Times during the 1900s about a fuel crisis, because in that time, everything was, the principal fuel was whale oil. And I mean, it's even funny today thinking that we already use whale oil as fuel, because today we've got fossil fuel. However, we are looking to our future and seeing that fossil fuel won't last that much. And we are trying to find new ways of generating fuel. And so let's research. And let's go. We've got to part 4, and we already are in cruise speed flight. The water for energy production. In USA, 80% comes from thermoelectric facilities and 80% comes from hydroelectric. So far so good, no water needed. Wrong, because in thermal power plants, we need water to refrigerate the work fluid, and most of thermal power plants use facilities like that, cooling towers, evaporative cooling towers that require water. That's an image from the Shearer plant in Georgia, and it's a very big thermal facility. That's another image from the Kraftwerk sorry for my Germany, Kraftwerk now that's right, power plant, and it works just beside the river. It's not by chance. It was built to use the river water. And here's the cooling tower I talked to you a few minutes ago. Here's the evaporation part of the water. So whenever you use a thermal facility power plant, you need water to cool down the vapor to go back and make more energy. And here's a Brazilian one, power plant from Engie. It works at a city called Tubarão, which is a word for shark. And just beside, here it feels like a river, but it's the ocean. It's using salt water to cool down the work fluid. But why is that? If you remember, you're in a master engineering program. And if you're not engineer, I'm sorry, I'm gonna be a little too engineered just right now. Pumps are equipment that hate multiphasic fluids. That means that pump hate water plus vapor. So if pumps works just with water, and after the turbine, you've got some water and vapor, because turbines hate liquids, pumps hates vapor. Therefore, turbine needs vapor, pumps need water, liquid. You gotta take the heat out of the vapor and deliver just water to the pump. That's called the Rankine cycle. You need to cool down the vapor after the turbine and before the pump. And that's the role for the cooling tower. It should cool down the vapor that comes from the turbine to the pump, and that use some water that evaporates and cool down everything. And every single thermal cycle uses water to cool down the working fluid. But then you ask me, Professor, come on, what about the Brayton cycle? That's the gas cycle. It burns gas with fresh air, and then it goes to a turbine, and the gas goes to the atmosphere. That's an excellent question. However, most gas power plants operating using combined cycle, which uses Brayton cycle in some part of it and uses Rankine cycle in another part of it, and the Rankine cycle needs a cooling tower. Therefore, we still need water for energy production. In US, water consumption goes just like that. For irrigation and livestock, 85%. For thermoelectric, 3%. Might not seem that much, but yet it is. 4% goes to mining, and 8% goes to domestic or commercial use. I mean, it does not seem that much, but oh, okay, Isabella, thank you for your participation. And the water consumption in US might not seem that much, the 3%. However, look at that return. You used 85% from consumption of irrigation and livestock, and then you get only 24% from irrigation and 56% from thermoelectric. How can that be true? I mean, because the livestock and the plants incorporate the water for growing. I mean, it makes sense. That cow ain't growing without water, and producing milk without water. And that water does not return to the system directly. We must consume it before it goes back using wastewater. And then it doesn't goes back anymore in this 24%. It goes back here in the domestic commercial, and it also evaporates, goes to atmosphere. However, the water used in thermoelectric, almost everything goes back to the system. So the solution is alternative energy that does not use water, right? Not exactly. Not for water consumption, even less for energy. When you are using hydroelectric power, we must count the evaporative losses. And so for hydroelectric power, it can go to 68 liters for every kilowatt hour. In thermoelectric power, it's only 1.8 liter for kilowatt hour. That happens because the reservoirs for hydroelectric power are really huge. I don't know if you ever have seen one, but man, that's a lot of water and it really evaporates a lot. So wait a second. We are not considering CO2 exhaust. We are talking about water losses. Even better, water consumed to produce energy. Using these only criteria, thermoelectrics are better than hydroelectrics. Okay, I'm not considering CO2. I'm not saying thermoelectrics are gonna save the country. I'm just saying that using evaporative criteria, thermoelectrics are better. A remark: water consumption by power plants varies significantly depending on the cooling water technology implemented. Open loop cooling consumes 1,000 liters per megawatt, cooling tower 1,800 liters per megawatt, and cooling reservoir 1,500 liters. But we have a different technology that can show us something different. It's air cooling. It's less effective, if you would call them liquid cooling, because liquid convection coefficient is about 1,000 times the air convection coefficient. Therefore, it requires a fan way too large, and it's not efficient for very big thermal power plants. I mean, and here I got another comparison for Brazil and US. It's the water requirements for clean energy production from different energy sources. That's a water consumed for 1 kilometer. Let us say my car is going to ride a 1 kilometer trip and goes, I'm checking the water consumed for that just from the beginning of the process to after my car go. The soy biodiesel consumes 353 liters of water, and that makes sense. I mean, you are growing a plant. After that, you are getting the grain. The grain needs to be processed to produce biodiesel. It really consumes a lot. In USA, you use corn ethanol, and it goes 158, and that also makes sense. The corn must grow. In Brazil, we use sugarcane ethanol. I know in Europe, you are used to beet ethanol, which is not that efficient, nor as corn, nor as sugarcane. But sugarcane ethanol, it's 98. Microbial biodiesel would be 40, and also microbial biodiesel in closed system. I mean, we are getting the effluent water, processing it, and putting it back, only 2 liters. There's 2 liters from evaporative losses during the way, because we need to dry the algae. It's very interesting. And also, conventional sources. I mean, all of these are alternative sources. However, when we go to petroleum, only 0.14. Let us check. water for energy production. Soy biodiesel, I know, alternative, very global warming efficient, but consumes this amount of water. Regular petroleum, 0.14. And then I go back to here that we are not considering CO2. And also, I go back, come on, I lost my slide about the fuel, but you were paying attention and you've got that slide of fossil fuels in your head. But okay, petroleum, coal with carbon sequestration requires this water, solar photovoltaics, this, and solar CSP, concentrated solar panel, this. All these forms of power generation require just a small amount of water. I mean, it's almost nothing, even more if it compared here. And that's because all you gotta do with this is sort of burn, just burn it. You don't need water to burn. Actually, water hinders the burning. And you are just burning a fuel. And this you are using solar. Okay, Jorge, please enlighten us with your wisdom.
Oh no, it's not wisdom, it's just a question. Where did you get that data from? Like, it's from a research paper?
Yeah, it is. It is from the Goody. I forgot to add that in the slide, but Goody got me this data here. The only work I had, and probably that's because I put Goody uses mile, uses gallon per mile. So the data is slightly different. And also Goody does not include the sugarcane ethanol, which I added here because I am Brazilian. In Brazilian, we use sugarcane ethanol, and it's way more effective than corn ethanol. And also, corn is food. We don't want to stop eating to produce fuel for our cars. Sugarcane is not food. I mean, it's delicious, but it's not food. I don't know if you have sugarcane in Mexico, but it's really nice.
Yeah, we eat it just like raw.
Yeah. So this just like the same. I converted the units, so we use liter per kilometer and not gallon per mile, but it's from Goody. Goody was a very nice research paper, and I really invite you to read that paper. It's a 17 pages paper, it's not that much. But it's very nice. And some of this class was based on Goody. Again, we are not comparing prices nor efficiency. I know all this process have different prices, and all this process here have different efficiencies, but even less considering climate changing effects. I know burning fuel fossils produce climate changing effects, and it's sort of changing all of our climate, but we are comparing water consumption. We are just forgetting a little the climate changing effects and looking to the water. Look to the water. That's what we are doing here. And that changes, that puts the petroleum or fossil fuels to a different perspective. However, solar seems a very nice alternative because it does not consume water, and it can generate some energy. It really can be very nice. So it's 11 half past 11. We only got half an hour. Are you tired yet? It's just one more part. It's like a marathon, and no one's gonna quit in the last mile. We've got opportunities for water conservation and savings in power plants. In US, during this Energy Information Administration from 2021, there were 1,860 operation power plants. 1,000 uses some type of water reuse. That's really impressive. I mean, I've got this report here, and good quoted a number for 2010. I was not satisfied with that number, and I went to the annual electric generator report from EIA, and I got this number here. It's really nice that all of these power plants reuse water. That means that we get these from the cooling tower, and the water here gets reused. It does not goes back to the river. It's just reused. It's really nice. And 100 uses dry cooling that we said it's not very effective, but it does not consume water. It's really, really nice. How does dry cooling work? It works just like that. Instead of using water or a condenser to cool the vapor, it was huge fans to cool the vapor. It's more like that. I mean, this one is a schematic, and that one is a sort of real facility. Those huge fans here are cooling the vapor that comes from below and putting it back to go to the pump. I mean, it's just a heat exchanger. It's just a big fan, a way too big fan, a huge one. And the vapor comes down here and the cold water goes down there. And that's because the vapor tends to go up, and it's easier for the pumps to get this water up here. It's a really, really huge heater with lots and lots of fans. I mean, it's not really not energetic efficient. However, does not consume water. If we are looking to water, well, it feels like a good alternative. But that explains why only 111 are using dry cooling. You won't want that. You just use that when you don't have water. There are some challenges because water density is like 10,000 greater than the air density, and also the heat capacity of water is way too big than the air heat capacity. Therefore, the air heat exchanger must be way too large than the water heat exchanger. They can be. I mean, if you have space, you can have these, but you gotta need some space. The size are like 4 to 6 times bigger than the wet system, and even worse, the cooling system depends on the ambient temperature, and that's a problem. Because when you got a summer day in Texas or a summer day near a desert, that just doesn't work. I mean, you got 40 degrees. I know the vapor is coming around 100 degrees, but you need cold water in the pump. You must not have vapor in the pump. Otherwise, you're gonna break the pump. And you are trying to cool down water 100 degrees to using air at 40 degrees. You won't achieve that. You're gonna need a cooler the size of your power plant. It's not efficient. But it's done in some places. However, when you are using water that comes from a river or something, it also depends the ambient temperature, but it depends less because water is more dense. I've got a few short story here. In Brazil, I've worked in a company that had headquarters all around the country, and I got here an image in Brazil with an annual mean temperature here. In South region, where I'm at, it can go to less than 10 degrees of average annual mean temperature, and in North region is more than 26. So the South headquarters, which worked here at Curitiba, had an available cooling tower. I mean, and this company just not throw away the equipment. They make it available for all the country. It was one just like that. So the North headquarters needed one exactly not like that. The power, everything was perfect. So why buy a new one? We've got this disassembled, put that in trucks. The truck goes up to the north of the country, install that in the North headquarters. Spoiler, did not work. Why? Why did that not work? Well, you are using an evaporative cooling tower. I mean, it's not just like the towers from thermal power plants. This was for industrial power plants, but in North is warm and it's also wet. This one was an evaporative cooling tower. Why did it not work here when it worked here? And the answer is quite simple. Here is cold and dry. Here is warm and wet. The water does not evaporate easily where it's warm and wet. So it was installed, it was not working efficiently. The company had to buy a smaller tower and to put it beside this one to make everything right. But okay, I'm saying that evaporative cooling towers do not work well also when using in hot places. But now imagine trying to use air. Man, you wouldn't need these. You would need 6 times these to make your process efficient, make your process work. And going to the end of our class, there's the use of wastewater as cooling water. Ew, come on. No one is bathing in wastewater. The proposal is to use domestic wastewater to cool industrial process. And that's not wastewater out of the house. I mean, you are not going in restroom and getting that wastewater and using the industrial process. It's treated wastewater with an acceptable water quality. We've got a study case in the Red Hawk power plant in US. It's a natural gas-fired project. It uses combined cycle, as I told you, as Brighton and Rankine cycle, works since 2002 and uses 24.5 million liters of wastewater per day. They are treated water from Palo Verde wastewater treatment plant. They are in Arkansas, if I so remember. It's in US. Also, there are interesting cases from the Pantelleria Island. The wastewater effluent was injected through a geothermal field to convert steam suitable for electricity production. And that can go to 100 megawatt power turbine. The Pantelleria island, it's an island near the Sicily, which is right around here between Italy and Tunisia in the Mediterranean Sea. And it's a very small island. Therefore, every water is very precious. So you can't just waste the water. You have to use everything you can. So the wastewater used to generate energy and also to cool the water. And another opportunity for water conservation is using seawater for cooling and then for water production. And that's a dangerous game. because water is used in more than one way, and seawater is a highly corrosive liquid, but it can serve as an excellent source for cooling water medium with some pre-treatment used in desalination plants. Since it's pre-treated, removed some of the salt to make it less aggressive medium, it really can be used. This is a video from the Tampa Bay seawater desalination plant.
In regions where fresh drinking water is limited, desalination plants remove salt from seawater, converting it into fresh water suitable for human consumption. There are more than 13,000 desalination plants worldwide, producing 45.5 billion liters of water a day. The desalination plant that produced this drinkable water is located right next to an electrical power plant which uses seawater to cool down its condensers. Post-cooling, the water travels via underground pipes to the desalination plant. Before salt extraction, the water is pre-treated in a multi-phase cleaning process. First, the water flows through screens which filter out large debris. From there, it flows into basins for the first pre-treatment stage. As large paddles agitate the water, the plant adds two chemicals: sodium hyperchloride, a disinfectant, and ferric chloride, a coagulant. The coagulant binds together sand and other tiny particles of debris, forming heavier clumps that sink to the bottom. This removes a significant portion of dirt from the water, but it's still far from being crystal clear. The water now moves into another set of basins for the second pre-treatment phase, sand filtering. Inside each sand filter, regulated by various pressure and flow gauges, a steady stream of air continually moves sand in a circular motion. The seawater enters at the bottom of each filter and flows to the top.
Okay. Windows does not want to play the rest of the video. However, you can watch this site here. It's from Tampa Bay Seawater Desalination Plant. It shows some of the process, and it really is nice because it goes from the salt water to drinking water, and it's not very much energy consuming. Then there go seawater for cooling and then water production. But why cooling water? Because the cooling water is discharged from the plant is 3 to 8 degrees warmer than the ambient source of ocean water. And Tampa Bay reports that when the power plant cooling is too hot for desalination membrane, that's very important. So the intake can be used to cool this water. I mean, there is no contact on that. If you haven't seen a heat exchanger, the contact is through a metal that in the side of the metal is cold and the side of metal is the warm, and the metal conducts the heat from one side to another side. A last opportunity for water conservation is here at Kenya, are dew collectors. It's very interesting study case here. There are plastic dew collection. I mean, there's no water here. It's really near a desert, and it can get almost 19 to 25 millimeters of water per unit. If you have lots of units, you can have lots of water collected from dew. It does not seem very much, but check this out. Whenever you got here the mean temperature, but also the total precipitation during a year, you can see that 19 to 25 is more than several months total precipitation during 1 month. I mean, they've got also April, March here with some precipitation, November, December, but June didn't have rain. 1 month without a single drop of rain. Therefore, this dew collector here can really help a lot. Well, we have finished the 5 topics, and that's what I was about to teach you. Several topics on water and energy and opportunity and research topic. However, the class is not over yet. I've got a few thoughts that I'd like to share with you. First, energy and water are increasingly interdependent resources, and they depend each other. It's a complex use because we've got agriculture, industry, transportation, social sectors that need them, like education, environment, health, and rural or regional development. Every single sector of those wants to have energy and wants to have water. And now I know we are having so much attention to the environment, but we must not forget all of the others. Probably and possibly the future is some sort of combined production. And it feels like these piled stones here, where if you can take one, everything will crumble off, and energy and water must walk together. And we haven't even talked about some real issues like microplastics that are polluting our water. They affect the water quality. It requires lots of energy to filter. I mean, if you have a filter with microplastics, you can throw away the filter because it won't be useful anymore. And it has effects in human and animal health. It's really a problem still under study and a problem to be solved to keep water quality. Another thought, and even more, it will be strong. Water and energy will be strongly dependent on the country needs. What does your country needs more, water or energy? What do you need? You gotta reflect on that. And because culture matters. Would you drink water from a machine that supposedly, it really works, but whenever a person just doesn't understand the process, would you drink from this machine that supposedly gets wastewater and give you clean water? But those guys from Senegal, they were very happy with that. And that's sort of importance, culture, because I don't think that machine would work in Brazil. I don't think people would drink this water here. Just because we have so much water, and we have regions that the water isn't good, but people aren't really willing to drink water that they know came from a wastewater treatment machine. If they know that came from wastewater treating machine, would you drink that? I mean, or would you be just like this Bill Gates here? It's sort of easier when talking about energy, but would you live near a nuclear power plant? I mean, every single day, wake up in the morning, you open up the curtains of your window and look at that beautiful cooling tower near something that you know it's a nuclear power plant. Even if there's no earthquake or seaquake or any other kind of danger, would you live there? Or would you rather live near a thermoelectric power plant burning diesel. Hey, there's no easy way out when you are talking about needs for water and for energy. Somehow, human presence impacts on nature. We need water, we need energy, and these resources gathering have impacts. How to reduce this impact is $1 million question. What will come next? There's no easy answer. A small reflection, and that I'm gonna finish our class. Everybody wants to save the planet and also the environment. So why do countries or companies keep polluting? Because merely it's cheaper to not treat waste than to clean it. And we are working to try to make it cheaper, or at least to make it profitable. So a speech will not solve it. I mean, there are some actors or there are some people who like to say they are defending the environment, but it won't solve just talking about. What will solve it is to turn waste into a business. Because doing research, we can really save the planet and the environment. By now, I hope you are thinking, man, how am I gonna solve all of these? You don't have to, at least not of it, maybe a small part of it. However, if I get together your small part, my small part, Jorge's small part, Raymond's small part, Isabella's small part, and it gets together, we really can do it. And I'd like to finish with a quote from the Project Hail Mary book, from Andy Weir. If you haven't read, I recommend it. It's a weird feeling, scientific breakthroughs. There's no eureka moment, just a slow, steady progression toward a goal. But man, when you get to that goal, it feels good. Yeah, it does. What was seen during this class was these 5 topics: energy for water supply and wastewater facility, wastewater treatment, opportunities for energy recovery. These 3 topics were together, water for energy production, and opportunities for water conservation and saving in power plants. These topics were together. I'd like to finish saying that there is hope for everything. Let's do research. Research will save the planet. And if you allow me, Kung Fu Panda rules. Yesterday is history, tomorrow is a mystery, today is a gift, and that's what it's called present, from Master Uguay. That's my contact info. If you have questions, if you have answers, need answers, we've got 5 minutes here. And thank you, it was a privilege to teach this with you. Jorge, did you have questions, or was your...
It was the emoji for applause. Thank you for the presentation. It was amazing, especially the use of those memes and like the man expression. I also use the man expression a lot. I think it's from South America and Central America. Just a really quick question. How long have you been researching on, for example, water treatment? And what is your bachelor?
Man, that's not a simple question to answer, because I'm electrical engineer. So I study applications of wastewater treatment since undergrad, and that would be more than 20 years. And however, my specific area of research is signal processing. However, again, at signal processing, you can go to 2 ways: to pure signal processing, which is a really hard math way, and you can go to application. I've always been an application guy. And so it was so many applications. I've worked with petroleum, with biomedical engineering, with materials engineering, chemical engineering, electrochemical signal processing, also use it to wastewater treatment, but also use it to fuel treatment, which was a very interesting case. And if you look for my name, you've got to find papers from orthodontics to porous media, and I'm in all this crazy stuff because everything is signal processing, and that's my passion. Now I'm studying more specifically wastewater, but it's really hard to say how long I've been to it. I've been to it since I'm undergrad, but I'm coming back to it again.
Okay, thank you. Then you have in like different fields, depending on like the research interest you've been having. Okay, thank you very much.
Lots of different points of view. I mean, it's nice. I'm a better professor and a better engineer because I have different points of view. I wouldn't say I'm a better researcher because of that, because anytime I'm learning a new stuff and publishing a new stuff, but that's a choice I've made way long ago. Okay, guys, I'm gonna stop recording just right now. I appreciate your presence here.